Now it's my great pleasure to welcome our first speaker, Professor Pankaj Joshi, my good dear friend from TIFR days, please. So Professor Pankaj Joshi is an internationally acclaimed scientist and astrophysicist. He is currently Distinguished Professor of Physics and founding director of the International Center for Space and Cosmology at the Ahmedabad University. Pankaj was earlier senior professor at the Tata Institute of Fundamental Research in Mumbai and also Vice-Chancellor of Charusat University. He is known as a scholar, a physicist, and an expert on cosmology. Pankaj's research interests are gravitation, astrophysics, and quantum theory. He has made fundamental contributions to black hole physics and cosmology with his extensive analysis of final fate of massive collapsing stars in the universe. This work, widely recognized for providing significant insights, led to the discovery that massive stars end up in powerfully exploding fireballs, also called naked singularities. His research is reported in more than 300 research papers in international journals of repute and books and monographs from Oxford University Press and Cambridge University Press. I do want to add a personal note that both books that Pankaj wrote, Global Aspects of Space-Time Geometry, and then Gravitational Collapse and Singularities, are books that many of us learned from and used. We have overlapped for more than 3 decades at TIFR. He was in many ways my mentor. I learned about gravitational collapse from him. So it's really a pleasure, sir, to welcome you and tell us about artificial intelligence and real intelligence and consciousness. Over to you, sir.
Okay, so as we were talking in the morning, learning about the universe, understanding the cosmos, that has been the quest of both science and spirituality. While I will tell about my work, which I think I'll try to orient it in such a way so that what are the future directions that could become or at least it is hinted at, so to say. Uh, you see, we have talked about quantum mechanics. We heard about it in the morning. We had some discussions on, you see, at least some mentions on consciousness in the morning. Most interesting aspect, as far as I can see, is science is in some ways converging to ask much more fundamental questions than it used to ask earlier. And that is why the title of my talk, namely AI, which means artificial intelligence, RI, you may not have heard, it's an abbreviation for real intelligence uh, or natural intelligence, as you would call it. And then, as I was alluding to in the morning, what is even at the root of what we call intelligence? How we make discoveries, actually. You see, scientists, since this is the conference which aims eventually to probe deeper questions, I take liberty to to ask even the question that how we discover at the end of the day. As I was saying, you you say that here is the universe and here I am. Here is the universe, here I am, and I understand the universe. I probe the cosmos. But then the quantum theory has actually diminished the distinction between the observer and the observed, so to say. The observer interferes at times into the observations is making, as was mentioned in the morning by Professor Dipankar Home. The bigger systems probe and measure, you see, the microscopic properties. So when you talk of, he briefly alluded to gravity, actually. Now, you see, let us take a stock of the situation. Uh, let us take a stock of the situation where we are. Uh, where we are. You see, general relativity abolished the distinctions between the space and time. Earlier, as you all know, most of you know, that for Newton, space was absolute, the time was absolute, the two were considered completely separate from each other, and then came the Einstein evolving this concept of the intermingleness of both space and time with each other. We can no longer think of them as entirely separate entities. On the other hand, came the quantum mechanics, probing the microscopic structures, the atom, the nuclei, the electrons, protons, so on and so forth. However, and I mentioned, you see, that we will try to take a review as to where we are standing as of now. Uh, General relativity as a theory has been very successful, again, experimentally and observationally. When you look out there in the skies, quantum mechanics or quantum theory have been very successful in the microscopic world and when we apply it. However, both the theories have extremely fundamental unresolved questions, or one could even say conundrums, you see, which are totally unresolved, so to say. Uh, Quantum theory has had foundational questions and issues right from the beginning, in fact, from the time of Schrodinger and Heisenberg and then David Bohm and many others. However, people sometimes take quote unquote pragmatic perspective. Just apply them to the systems, do your work, proceed. And then many applications were discovered. However, as we all know, the questions remained. They were not attended to. Everyone knew that there are questions. Similarly, in Einstein theory, there are very fundamental unresolved questions. One of them is relating the information paradox for black holes. You may have heard, of course, about the black holes. What they are, I'll try to tell you a little more. Uh, but the point is, the black holes eat up, you see, everything. And is information really destroyed by the black holes? If not, then how do you resolve it? Now, there are many other such questions. What is the final state of a massive collapsing star? Okay. maybe I should go ahead and then come back to this uh, issues. What is the final state of, you see, massive uh, collapsing stars? If you want to ask that particular question, then in that case, you see, in that case, what happens really is that, right, you see, there are stars which are much more massive than our own sun, 10 times, 20 times, 30 times the mass of the sun. Uh, the sun is here. And then there are such bigger stars such as Sirius, Pollux, Arcturus, and so on and so forth. Sun, what will happen is it is giving so much of energy and heat. It has lived some 5 billion of years so far, and it will still consume its fuel for another 5 billions of years, and then that will be the end of the sun itself. Its outer layers will expand, engulf the earth and the Mercury and the nearby planets, and you see that will be the end of our own solar system. But the star, if it is much more massive, then if it is much more massive than the sun, you see, such as this one or this one, then such stars burn much, much faster than the sun. They would survive only for a few crores of years, 20, 30 million of years. So they will burn out very fast. What will happen to such stars? So this question is the origin of all of black hole physics. So a very fundamental, I mentioned, you see, I was mentioning the basic unresolved questions in quantum theory as well as the gravitation. So it was assumed by Stephen Hawking, Roger Penrose, and Kip Thorne, and many eminent people that all such big stars, when they run out of their fuel, they will become what is called a black hole only. But this conjecture, called the cosmic censorship conjecture, in the name of Roger Penrose, continues to be unresolved and not proved, and it's an open issue. Now, it is such a fundamental question that this huge black hole physics being applied, you see, for all the astrophysical considerations and the jets from the centers of galaxies and whatnot, gamma ray bursts, all these are all cosmic phenomena. So, that at the very basis of that, this question remains unresolved. We have worked out, of course, many models where the stars actually, very massive stars, do not become black holes, and that is, work that is in huge debate internationally. But right now, I was focusing on unresolved issues, and still much more unresolved and fundamental question is that of, you see, the unification of general relativity and quantum theory. Quantum theory, very successful. General relativity, very successful theory. But then their mathematical frameworks are so extraordinarily different from each other. Quantum theory deals with operators and, as you see brackets, bra and cat, and you see various other principles such as the uh, evolution, time evolution. But all of quantum field theory and all that is all in flat space-time, a space-time which is technically called Minkowski. And you can ask me questions later if you have any questions, because before general theory of relativity, there was the special theory of relativity, and that is a space time which is completely flat. And quantum mechanics operates basically there. And since it's a very local theory, we don't, you see, realize the effect of the so called curvature of space and time, which manifests itself on a very large scale in the universe. On the other hand, the mathematical framework of general relativity is so different. It is based on what is called Riemannian geometry. I think after such a nice lunch, talking of Riemannian geometry and you see curved space times and all that, uh, it was mentioned by the anchor, I think it may create some excitement and hopefully. But you see, it's all curvature of space and time. Now, this is totally, you see, mismatch with the mathematical framework of quantum mechanics. As a result, what happens is that both the theories remain, uh, uh, you see, totally different from each other, mismatch from each other, and three fundamental forces with the help of quantum mechanics, quantum theory, quantum field theory, we have unified, namely the electromagnetic forces and weak and strong nuclear forces, and then we have large hadron collider and so on and so forth. However, gravity remains totally a separate issue, totally non-unified kind of uh, you see perspective. How do you what do you do? I mean, where do we go? What direction we take? We had a huge effort on string theory. You all have heard about string theory, right? Raise your hands. Those who have heard about string theory, wonderful. Now there have been other efforts also, which is called loop quantum gravity. String theory is one theory which is trying to unite the gravity with other forces, but there has been another effort which is called loop quantum gravity. How many people have heard about loop quantum gravity? At least few people, if not so many. Maybe because they are competing with each other, they always fight with each other. Uh, you see, so by the way, I have seen real fights happening in conferences where only blows were spared. People shouted at each other. On one hand, the string theorists, and on the other hand, the loop quantum patriarchs. But the important point is, after many years, we realize that none of these theories are also working to unite what they were trying to do. It's a very big goal, actually. So if you fail, it is not a surprise. Uh, Especially string theory, so much effort. I mean, brilliant of the brilliant people have tried their minds, but they were simultaneously starting to do cosmology as TP. We call Professor Singh, you see, TP. So I just say, I am very grateful for your very kind introduction, and it is such a pleasure that we are here together. Uh, so you see, very brilliant people tried this string theory. Very good people, very brilliant people tried the loop quantum gravity. What I am trying to say is problem remains unresolved. So what I am trying to do is I am not highlighting to you the successes of science, but I am highlighting to you the huge problems that we are facing today. We are having some successes, which is fine. Like even Newtonian theory is all right if you want to work out, you see, the satellite orbits and when you want to calculate the planetary motions and so on. So at very finer levels, the corrections manifest. But that doesn't mean that the Newtonian theory is wrong. What it means is it applies up to certain regime, then the general theory of relativity takes over. Similarly, quantum theory, despite these foundational issues and problems, which will add much more. I mean, at some practical levels, you do your day-to-day work. However, however, the question that we want to address is that what is the fundamental nature of particles, the world of particles, the world of, you see, stars actually. What is really happening in the world of stars? What is happening in the world of galaxies? So when you are asking such questions, then you are, you see, compelled to go deeper. Now, you see, I am taking slightly different turn, just trying to be, you see, little more thought provoking. Uh, I mentioned in the morning that there are big developments on which go under the name of artificial intelligence. Okay. Now, then I said that the question that is being asked is when you say AI, what is really the I? What is really the intelligence? And then I also mentioned that scientists really did not think much about, you see, what is intelligence, what is discovering. See, sometimes you say that, oh, the world is mathematical and it is mathematics that is manifesting itself. And then you just find the laws and you say such things. But then who is perceiving these mathematical symmetries? Who is perceiving? It is you who are detecting, right? That yes, here is the mathematical symmetry, or here possibly some violation of that symmetry, so on and so forth. And quantum mechanics has been very forcefully highlighting the role of observer. I think somewhere in the morning the name of Tagore was also mentioned. Einstein was, of course, mentioned, but there is a wonderful dialogue between Einstein and Tagore, if you have heard about it. Oh, how many people have heard about this dialogue? At least a few. That's good. Uh, so they had a detailed meeting, not one meeting, but I think more than two or three meetings. And they extensively discussed, yes, how many? Four meetings, yes. So you see, in those meetings, it is extraordinary. Those of you who are, who have come here, so you might like to see and figure out those things where the nature of mind. You see, I bring in the word mind because now it is coming very much under the scanner of science. The Scientific American magazine has actually a special, you see, uh, subdivision, that is Scientific American Mind. Now, why this question? Because as I said, when you talk of intelligence, then you ask, what is intelligence itself? And then, what is mind? See, scientists have started slowly, slowly. See, scientists are always very slow in doing anything because they have, with lot of hard work, you see, made their basis ready. So if you ask them to change anything, they will be extraordinarily conservative. They don't change. Uh, and that is why they sometimes are even blamed, you see, materialistic and this and that. But not really that way. It takes a long time to create, a solid intellectual base based on which you can, make further deductions. And when those deductions are verified, uh, But the point I was making was that now, because of artificial intelligence, what is intelligence and what is mind, these questions are being asked. Earlier, when I met some of my psychologist friends and asked, what is mind? They would say, never mind. Okay, so what I mean to say is that for most of the scientists, mind was really a collection of all the effects and the feelings and vibrations that the brain is creating. See, our brain is always interacting with the environment. When you are eating, you see, and when you see the ice cream or when you see the mango, then your brain reacts in a certain way, as you have just experienced. And then if you are too full, you will feel that maybe it would have been better if I did not eat this and, finished this. The point is that the scientists have taken the cumulative effect of all the interactions of brain as mind, but then there have been deep problems with that. Now, I would like to put forward a hypothesis. What hypothesis would I would like to put? This hypothesis, I would like to say that when you talk of, okay, the more precise statement I'll come in a moment, but I would, first say the following. When you're talking of mind and all that, then the ancient Indian traditions have said so much about mind actually. If you see the Patanjal Yoga Darshan, for example, then there is a whole lot of reference of different states of mind and the sanskaras and so on and so forth. So, what I want to tell is that the Western scientists are now already writing papers on what mind is. Sean Carroll, for example, he was at Caltech. He has written a very detailed paper on consciousness and the physics laws. And he has pointed out that how the current laws of physics are inadequate to go to it's a very detailed study. Whether you like it or not, it is up to you, but I would urge you to have at least a look at that. He is trying to correlate the modern physics with the issues of consciousness. And quote unquote, what is consciousness? It is something that nobody knows. And that is why it has been called the hard question of consciousness. Uh, so, uh, the point is already, as I pointed out in the beginning, the laws of physics are incomplete, even though we practically use them. They are already incomplete. There is an incompatibility between the gravity and quantum theory. Now, as far as mind and intellect and all those things are concerned, they have absolutely or practically nothing to say. So, here the point that I would like to, make is that if you look at the Indian traditions, in fact, the mind itself is nothing else but a form of matter. Mind my statement while I am talking on mind. In Indian tradition, it has been called antahkaran. What we call mind, it has been called antahkaran. And you see, other than the consciousness, all the rest of the entities, That is, you see, the usual earth and the sky and the chemical elements and everything, then going to subtle levels, the mana, buddhi, chitta, and ahankar. These are all ashta prakriti. Bhumi, rapo, nalo, vayu, kham, mano, buddhi, revacha, ahankara iti yam mein Bhinnaha Prakriti Ashtadaha. So it is eightfold Prakriti. Prakriti means we can roughly translate the world of matter, so to say. So the hypothesis that I was alluding to was that mind itself is an extraordinarily subtle form of matter. Probably it is the form of matter which we have still not probed at all. Large Hadron Collider and so on, we all know that they have done great things, but it has extraordinarily, compared to the huge energy scales at which so-called quantum gravity will operate, the Planck energy scales, compared to that, it is nowhere in the, consideration. So, the form of matters we have probed so far are perhaps very, very limited. We have only gone up to the level of, elementary particles. But there could be much more subtle forms of matter, so to say. If at all, you take cognizance of what I said about the Eastern traditions, okay? If at all you want to take cognizance of the Indian tradition and the texts which have been referred to. So there it has been mentioned, you see the matras, the tanmatras, so they have been mentioned as, you see, much more subtle form of matter. Now, we don't know the quantum gravity anyway today as of now. So, who knows? We have to know the matter much, much better than we do know today. Knowing so far may be just a first step, actually. Still, we have to explore the matter itself a much finer level, and then we can understand mind much better. And then, who knows? The mind itself may be a quantum entity. When you view from this perspective, the mind itself might become, but that will be entirely revised quantum mechanics, okay? It won't be the somewhat incomplete theory that we know as of today with huge number of foundational problems. So that is where you see the laws of quantum gravity may be available. This is only, as I said, hypothesis because of the failure of string theory on which, you see, best of the best people, best of the minds, you see, have worked for, I think, what, more than 30, 40 years by now. So, you see, I was with Stephen Hawking actually in Cambridge, sitting in his office, and I think it was sometime in 1980s. I was sitting there and I mentioned to him some fundamental problems in relativity and especially the cosmic censorship problem. Whether every star will become a problem. I mean, the problem that whether it will, be a black hole or what we call a naked singularity. This problem I was discussing with him. He told me, don't do this problem. Don't do this problem. It is very difficult. You just go downstairs because the Cambridge University press offices were just downstairs in his college. He said, green books have come out. Green, Schwartz, and Witten, 3 volumes of string theory. They had just come out, Green, Schwartz, and Witten. He said, just go, purchase those books, start studying them. and then you see you will make a career. Uh, you know, Fortunately or unfortunately, I didn't follow his advice. Uh, and I continued to work on the death of the stars, which I think we have enjoyed. And Professor Singh has been one of our very close collaborators on those researches, and our papers are highly quoted in that arena. But what I was trying to say next was that what a scientist will do. You want to probe this kind of, you see, depths of matter. The new laws that will be applying to both quantum as well as gravity. If you want to probe this kind of laws, then one path I told you was, you see, the very subtle forms of matter, but that is only a hypothesis, that is only a conjecture. How actually you will do that? So that is where actually, and this is the final point of my talk, that is where our own research is, I think, somewhat leading or showing the possible way. You see why string theory has failed, why loop quantum gravity has failed, and what do you do? What do you do in order to? What do you do in order to, so to say, do the new physics? So, what you have to really do is that you have to probe those regions of the universe where you see gravity as well as quantum, both of them will work together. And such regions are the regions which occur in the very final stage of gravitational collapse of a star. And here I throw in at you a new term, space time singularity. What happens to a very massive star when it collapses? Roger Penrose showed, and he was given the Nobel Prize in 2020, I believe, for that. He showed that general relativity shows that that will become what is called a space-time singularity. A singularity is such a, uh, such an epoch, such an event in the cosmos where all the physical quantities like the densities and the temperatures and the pressures, everything will blow to infinity. Now, such a singularity, according to the cosmic censorship conjecture, will always be hidden within the black hole, according to the Hawking and Penrose and that hypothesis. But our work has actually showed that such singularities can be actually visible. They can be visible in the sense that they are no longer covered within the event horizon of the gravity. If that is the case, then that is the place where actually quantum and gravity are working together. They are operating in unison with each other, and then it is the observational signatures from, you see, those entities. Only that can tell you how the quantum gravity will operate. We have tried purely theoretically in a very big way, string theory, loop quantum gravity, other possible theories. But the thing is, now the opportunity is really to, so to say, probe the ultra gravity regions, which are the singularities. So, just to end my talk, you see, this is the collapse of very massive stars. Those of you who are interested, you can see my cover story article in Scientific American, where the physics of this singularity is not hidden within the event horizons, is, you see, explored. And then my Oxford book. Uh, the story of collapsing stars, because once I wrote this Scientific American article, from all over the world, students and even eminent citizens wrote, and so much interaction happened that I thought it is a good idea to just put it in this book. So what I mean to say here is that it is this observational effects, if we study them more carefully, then that could give us a better clue to a possible uh, plausible quantum theory of gravity. Uh, String theory failing, look, quantum gravity failing, so far many other attempts failing. Maybe if someone is extraordinarily hopeful, still another theoretical effort may be made. Uh, but you should, know the history so as not to repeat history. Uh, in my view, since there is a very strong theoretical foundation uh, of existence of such regions which are existing outside the uh, horizons, you might be able to capture them, study their observational signatures by means of LIGO, or you see the I'm sorry, Event Horizon Telescope pictures. I was searching for them. But anyway, let me just tell you, because I think my 5 minutes are left. So I think basically I have told you, you can see those details probably in one of the references. It is the, you see, Event Horizon Telescope is a collaboration of NASA and Harvard and others. They are they are actually uh, they are actually probing, you see, the center of our galaxy, the very center of our galaxy, and they are you see, taking pictures of this central region, trying to find the event horizon or a black hole there. So there again, their series of papers, they have cited our works, as TP and I and Haridas, we were talking some time ago. They have cited our works in some detail. That you see, trying to fit that model with black holes is leading to some problems. But the naked singularity could be an excellent black hole mimickers. Just to conclude, to study the very finer forms of matter, or to study the very subtle laws of quantum gravity, we must explore those regions in the universe where those effects are actually taking place. How do you make the laws of planetary motion? First, you observe the planets. First, you make measurements. Oh, Tycho Brahe, and what did they do? They created, huge data banks, right? In our modern terminology. Then the laws came in. So similarly, it is there, same thing has happened in many other areas of science. Similarly, here also you must create a data bank of such regions in the universe where actually quantum gravity is operating. Then you will know the best of the form in which the matter is working, the subtle laws of the operation of matter, and who knows, I mean, where this issues such as what is mind, and the what is quantum gravity, and what is really the ultimate laws of physics, if they all converge, and that is what physicists always want. They want everything to converge. You can ask why not remain separate and diverge, but physicists have this urge. So maybe this is one opportunity to probe the laws, ultimate laws of physics. Thank you very much.
Thank you so much, Pankaj, for sharing your deep insights in a very friendly and lucid manner, going from artificial intelligence to real intelligence, and also your own distinguished work on end state of stars. So we have time for a few questions. Um, so as how many? Two questions. So there are two questions from the audience. I will read it out. First question is, since gravity is somewhat responsible for formation of complex structures in the universe that was initially smooth, could it be that gravity is necessary also for consciousness to form?
Uh, I would maybe it is, but I would say that it is the combination of all the forces, all the observable forces in the universe that could possibly be responsible for uh, you see the phenomena which we call quote unquote consciousness. Gravity, in the limited sense of the word, probably alone may not be the entity which may do the full job. We already know you see, if we by gravity mean its theory as general theory of relativity, then we already know certain incompleteness of general theory of relativity. So maybe we have to go beyond GR.
Yeah. Could I just, since it's on consciousness, when you were talking, did you make a distinction between mind on the one hand and consciousness on the other? You talked of mind as a very subtle state of matter, but at that time, I did not find you saying anything about consciousness. You made a distinction?
You are quite right, actually.
Mm.
By consciousness, I meant what is something as even at the basis of the mind.
Yes.
I meant that, and it's a very good point that you have made. Uh, Mind, I meant to imply as a purely quote unquote gross matter. Whereas consciousness, if you ask me to say more about consciousness, then it will be too much of, for my sort of, I mean, because I would like to speak on scientific evidence. So there is not so much that we can say. And that is why I mentioned about probing this regions, you see, where this quantum gravity phenomena might be occurring. But yes, I meant the two to be separate from each other. And mind is, yeah, that's right. Yeah.
Thank you, Pankaj. Yes. So we have a second question. Given the intriguing prevalence of Fibonacci sequences and the golden ratio across various scales, from macroscopic biological structures to microscopic quantum phenomena, for example, even in some theoretical models of quantum gravity. So, given the prevalence of Fibonacci and golden ratio, does the speaker see any viable pathways or theoretical frameworks where this observed symmetry could provide a deeper insight into reconciling quantum theory and general relativity? Role of Fibonacci sequences and golden ratios and their prevalence in nature. Could this help give a deeper insight?
It's an interesting point. The uh, so called quote unquote fractal universe has been explored in some detail, trying to find what is mathematically called self similarity. Uh, but I'm not sure how far that attempt has gone so far, whether we have been able to actually take it sufficiently far. In principle, in principle, any one path followed sufficiently deeply should take us to what is unknown. This is in principle. But the important point is that for any given path, such as, for example, this Fibonacci sequences or fractal universes or self-similarity. People have tried somewhat, but they have not been able to make sufficient progress. Uh, People have tried, as I said, you see, bigger things like string theory and loop quantum gravity to reach to quantum gravity, but even they have so far not succeeded. So I would say that to my mind, real possibility would first to learn, you see, observations are the key thing. Look at the regions where quantum gravity is actually operating. We, in principle, know Big Bang, you see. Big Bang is a singularity, and that is also a naked singularity. And all that we are observing is the outcome of Big Bang. But then we have to have a proper theory to really conclude what early universe was actually like. And the theory we made, namely the Friedman Robertson Walker universe, that ran into huge problems. And then we have inflationary paradigms, and there again, total non uniqueness. We don't really understand the behavior near the singularity. So, those are the observational effects, and a catalog of those effects would be, in my mind, the best. Uh, Venue or best direction to follow.
Quick, one last question. Yes.
Or as arising out of the interaction of many different parts of a complex system. Is that viewpoint more comfortable with you, or do you think Tegmark's view of as a new state of matter that can process information?
You mean consciousness as an emergent phenomena in some sense?
I think that's what Tegmark meant in that paper, although I'm not sure, sir.
Yeah. This has been suggested. You see, sometimes they say that, the sum is much bigger than the single entities, and it's things come together and they behave, or they give overall output in such a way which we interpret, quote unquote, as consciousness. This suggestion has been made, and I am fine with it. But as they say, you see, the proof of the pudding lies in testing. So, if we are, able to make some further predictions and explain now in the domain of, you see, AI and so on, apply some of these things, then that will gain more credence. Otherwise, it will be another hypothesis.
Okay, sir. Thank you so much, sir.
Yeah.
Thank you. Thank you.